Hello, students. Taking a look at section 8.3. It's on functions. Again, this is something you have seen in the past. We build up to it. It is a culmination. Many of you may not be teaching this explicitly in your classrooms to your elementary school students. But again, it is something Common Core does have it listed as all the way up through grade 8. However, what I want you to see is this. It may be a grade 8 topic. The reason why it's included in this course is because you as a teacher need to see where you fit in the process of creating this. So everything we've done earlier on, we've actually used functions. We just didn't explicitly define them. So we're going to demonstrate them now and show you how you can use function ideas earlier in the grade levels than grade 8. Grade 8 is when we start looking at more of a function notation. Okay, so a function is a very specific type of relationship. We'll figure out what that terminology is, but there's a lot of ways to represent them visually. We can represent them as a rule, as a function machine, like a picture, as an equation, a diagram with arrows, a table, an ordered pairs, and also we can do that visually with a graph. Okay, so a function is known as a rule between two sets. And so if you want to take a look, you can start to kind of figure out what people's rule is. What are they doing to get from one set to the next? How did they get from the first to the second? And you might be able to say, well, wait a minute, for this first one, it looks like every time the student said a number, the teacher multiplied by 3. Okay. Now we get there by looking at all of the values, not just one. If we looked at just one, you might have thought, aha, they're just adding 2 because 1 plus 2 is 3. You're not wrong, by the way. You're not wrong at all. We just realized, hey, let me check the next one. And if we tried adding 2, it doesn't work. So we have to have a rule that fits for all of them. And again, there might be many possible answers, but in this case, one that works for all 4 of these is to take the student's number and multiply it by 3. Now we can say that in words, multiply the student number by 3. We can write it as a symbol, and we could actually have the teacher's number is the student number multiplied by 3. Okay, so this would be more formal function notation. All right. Now let's move on with a couple more pieces. We can actually look at functions as a machine. The idea being that we take a machine that puts something in and gets something out. Okay. Now this notation that we get out is called function notation. So function notation, we tend to write it as f, which is the name of the function. And we tend to write parentheses, and then we always write what your input value is. So oftentimes your input value would be x. And then afterwards, we write what is the output from the function. So if your function was to add 3, then you would take your input value and add 3. And that would be how we'd write it function-wise. So what we do is we'd say, okay, let's take the number 0, for example. What is the function of 0? It's a fancy way of saying what's the output from the function when 0 is the input. Don't forget, that's the input. So what do? We add 3 to it, and we get 3 out. So my final output would be 3. An input of 0 gets me an output of 3. Now you could think of it as like 0 goes into this machine, and out pops 3. 0 in, 3 comes out. What happens when I put 4 into the machine? Okay, I'll choose a different color here. So here comes 4. 4 goes into the machine. Add 3, and 7 pops out. Oh, it's a machine. It's like a vending machine, right? You put in your money, you put in $1, and a soda pops out. There's your input, there's your output. Okay. All right, let's continue on down. Now, you could also write this as a table. So notice X is the input values, and the next column, the F of X, is also known as the output values. So output of 3, 4, 6, 7, and 9. Now you can recognize them here as an equation, but the key piece to a function, it's a relationship, right? There's inputs and outputs. And a function is a very specific relationship where exactly one output gets paired with each input. So each input that you have, like 0 here, right? 0, that's an input. Each input that I have maps to exactly one output. Okay, there we go. So the number 1, that's a different input. It maps to exactly one output. So here's what we can't have. Okay, I'm going to show it to you as an arrow diagram. Okay, so if I had 0, 1, 3, 4, 6, and over here 2, 1, 7, 8, 5, 0 mapping over to 2, you're good. That's just fine. 1 mapping over to 2, excuse me, that is also okay. Now you could say, but wait a minute, it says there's exactly one output for each input. And I would say, yes, for the input of 0, there's exactly one output. Let's go down here and see how this could be a problem. If I take the number 3 and I say, 3 takes me over to 7, 3 also takes me to 8. This picture right here, where 3 goes to 7 and 3 also goes to 8, this is where it fails to be a function. Okay? Each individual input has to map to exactly one output. They don't have to map to a different output. They could all map to the same output, but it has to map to exactly one. Okay. That's the definition of a function. Now you can picture this. I mean, in real life, where would you see a function? Your cell phone bill is a function of the number of minutes that you talk on the phone, plus the number of text messages you send, plus the amount of data you use, or something along those lines. So from 1 month to the next, if you sent 500 text messages and you used 3 gigs of data, you would get charged a certain amount. The next month, you, using the same amount, would get charged the same amount. So imagine how frustrating it would be if 1 month, right, maybe, I don't know, maybe your text messages are all free and it's just about your data. Okay, so if you just used 2 gigs of data, right? You're like, sweet, I used 2 gigs of data. And they charge you the first month, they charge you $40. Then you use the exact same amount of data the next month, and they're like, okay, it's $60. You're like, wait a minute, how come it's different? Right? So you want things to be a function for the same group of inputs. You want to get exactly the same output. Okay. All right, so let's talk about the definition of a function. A function is a set in which each element of A, those are your inputs, is paired with one and only one element of B, and those are your outputs. A is known as the domain of the function. It is a set of objects, and B is the codomain, which is where you're kind of mapping onto. Now, just be really careful here because there's another word that is used, and if you've done some stuff with functions in the past, you might remember that word, and it's called a range. Okay, so again, if I had a 1, a 2, a 3, a 4, and a 5, those are my inputs. And over here, I had a 5, 7, 9, 11, and 13. Okay, 1 goes to 5, 2 goes to 7, 3 goes to 7, 4 goes to 11, and 5 also goes to 11. Then your domain, which is the set of all inputs, okay? Your domain would be the set 1, 2, 3, 4, and 5. Your codomain would be this entire set of all the possible things, a 5, a 7, a 9, an 11, and a 13, okay? Notice I'm going to put a little note here. Those are all the possible things. When you start talking about, hey, what did we actually map over to? That is the range. And the range in this case would just be a 5, a 7, and an 11. So typically, if you were taking a class, like an algebra class in high school, or maybe even middle school, depending on where you took it, you really are focusing mainly on the domain and the range. The domain is the actual inputs we're using, and the range is the actual outputs that get hit. Now, your calculator is basically a function-based calculator. If you give it an input like the number 5, you press the squared button, that input is going to give you exactly one output. Imagine the frustration, right? If your calculator was not a function and it would give you multiple outputs. So you're like 5 squared and it says 25. And you're like 5 squared. The next time is 37. And you're like, wait, what? And imagine even worse if both of those were correct. That would be absolutely crazy, right? So that's the idea. We want things to be functions. Functions do make it easier for us. We do turn this into some word problems. You can kind of get the idea that functions often are based on variables. So if you're doing manufacturing of bicycles, then you might have something like profit, and you might have revenue, and you might have cost. And all of those depend on how many bicycles you produce. So if you're producing X bicycles in a day, right? Then we could see how much your total cost is. And here it says the cost is $1,400 just to rent the space, and it's a cost of $500 per bike manufactured. Okay, so your costs are going to be 500 times the number of bikes that you build, plus the fact they had to pay for the space for $1,400. If you sell the bike for $700 each, they didn't mention this, but that's your revenue. So you could have a revenue function. My revenue based on bicycles produced would be 700 times the number of bicycles that I produce, 700x. So now I have cost, which is 500x plus 1400. I have revenue, which is 700 times x. And then I can even have profit. And if you think about it, profit is made, think about Shark Tank, right? Take all the money you bring in and then pay your expenses, which is your cost, and whatever's left is profit. So the profit function would be the 700x minus 500x plus 1400. Okay? If you want to simplify that, you can. It would be 200x minus 1400. So if you picture that, then yeah, if you sold 7 bicycles, right? 7 times 200 is 1400. You subtract 1400, you're at 0. You broke even. If you only sold 1 bicycle, 200 times 1 is 200 minus 1400, you lost $1,200. That is not good as a business, right? Okay. So I want to show you though, I'm going to jump over here to Desmos because I believe it's a really powerful tool. Okay, and what I want to do is show you, I'm going to go to the graphing calculator option, and I'm going to type these in. I'm going to say C of x equals 500x plus 1400. Okay, and then I'm going to say revenue of x is, what do we say, 700x, right? Okay, now here's the thing. We really can't see much. 700x means if I go over 1 unit, I go up 700. That's like the slope, right? So I need to change my graph settings. My y-axis, maybe I need to come up here to, I don't know, 1,000, 1,500, maybe 2,500. Okay, so I just want to show you, this is kind of what I'm talking about. It's a little ways over, right? So in order, now I can actually see a slant in the curve. So notice if I go over 1 unit, I would go up 700 to get that revenue. Okay, 1 more bicycle from here, 1 more bicycle brings me up another 700. Now I'm at 1,400 for 2 bicycles. Okay. So now I'm just going to zoom back. And that's why I love a program like this, because it's a little bit easier to kind of see. Take a look at this, right? If I click on the line, there's a dot where they intersect. That's where the cost function hits the revenue function. And they're telling me it's when my input is 7. If you sold 7 bicycles, you'd have $4,900 in revenue. But if you made 7 bicycles, because your $500 cost per bicycle, plus your $1,400 that you spent having the shop open, that's also $4,900. So everything before that, if you sold 1, 2, 3, 4, 5, or 6 bicycles, you are losing money. At 7 bicycles, you break even. You have 0 profit. your revenue and your cost are the same. But after that, you sold another bicycle, you sold 2 more bicycles. Now all of a sudden we're into the profit range. The blue curve is higher than the red curve. Okay. Now take a look at this. If I put a profit function in here, I can actually just say R minus C. This right here, this green line is my profit. So if you take a look right here, this is measuring the profit. If I do 7 bicycles, remember my revenue and my costs were both $4,900, but they subtract each other out and I'm left with 0 profit. If you click on this line, you can start to see what happens if I sold 20 bicycles. I'd have a lot more revenue than I do cost, and I'd end up with $2,600 in profit. But likewise, if I was down here in the negative, I only sold 5 of them. This is bad, right? If I sold 5 bicycles, I've lost $400 because of the overall cost of all of that. Okay. So if you've ever watched Shark Tank, you'll hear them say things like, what's your revenue? What's your margin? The margin is saying, if I sell another bike, how much more do I make? The margin here would be $200 margin. Okay. But you still have to you got to eat the extra cost of just opening the shop up. And that's why businesses are expensive. Okay. Let's see here. So I kind of already showed a few arrow diagrams. You'll represent a few of them here. Students have a chance to do this up through grade 8, but you'll also see it in earlier grades as they're making connections between ideas. And so here we go. Now notice, in order to be a function from A to B, every input has to have an arrow going out. And remember, if they have an arrow going out, it can go to exactly one output. So maybe, like, for example, this one right here, I can see number 1 has 2 arrows going out of it. Not a function. Over here, question B. A goes somewhere, C goes somewhere, B doesn't go anywhere. I'm sorry then, it is not a function of A because every element has to be mapped. Okay. If you were to say, Scott, but what if? I love the what if questions, by the way. Keep them coming, keep them coming. What if I scribbled that one out and it didn't exist at all? Well, if it didn't exist at all, then it is a function because every one of your inputs maps to exactly one output. Okay. All right, there you go. So here, John and Joan, maybe this is the relation of last name. John and Joan are both named Brown. Mike Smith and Sue Doe. Sudoku. Sudoku. It's a puzzle. So notice everyone maps to exactly 1. Even though 2 people map to Brown, that's okay because John mapping to Brown and Joan mapping to Brown does not violate the definition of a function. Each input has to go to exactly 1 output. Okay. There we go. Determine which of the following are functions, blah, 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 blah. Then we have functions as tables. If you look at it as a table, like an X and a Y, you can do that, right? Inputs and outputs. So input advertising, output is sales. You could also do it as ordered pairs. I guess I should come up here and say that. So here's my X and my Y. And again, you've done this when you were graphing points, but here's X, here's Y. So that gives you an ordered pair. And again, if you wanted to look, is this a function? Like if I said a bunch of ordered pairs, you'd be looking to see, does each first number map to exactly 1? And the answer would be, in this case, yes. So it meets the definition of a function. Okay, so they give you a few to practice on with those. And then they say, hey, let's do them as graphs. And again, what is a graph? It's a visual representation of the ordered pairs. That's all that it is. So when you have a graph, it's like a connection of all these ordered pairs. If we're using terms in a sequence, like we did back in chapter 1 and 2, and then a little bit more recently with arithmetic sequences, the term number, like the first term is 3, the second term is 5, the third term is 7, right? You get this beautiful connection and you have a really nice relationship right here. So this would say the nth term is 2n plus 1. That's fantastic. You might as well call that a function of n Because now you can see you have a slope of 2. That was our common difference previously, but now, based on what you know about slopes and lines, you can see the slope of 2. A little bit of a caveat, a little bit of a warning. When you are doing arithmetic sequences, you could not put in 1.5. 1.5 would not exist because we're only doing the actual terms. Notice here the dotted line. If we were doing a function where the inputs were real numbers, any real number, then you'd have a solid line because every point on that line would work. So that sometimes you see a little bit of a difference. You're like, sometimes it's just the dots. How come? And it's just the dots because that's the definition. Okay. And this is a graph. We should be able to read a graph like this, right? So why a rental car company would not set rates as depicted in this graph. Okay, why would they not set rates like this? So picture, right? So again, if I rented a car for half of a day, it'd cost me $50, looks like, right? If I rented a car for a day and a half, well, I've got a pretty serious problem. Am I paying 50 or 85? Like I don't know which one I'm paying. It could be either one. So this would be really, really bad for a car company. And also for you. Well, how much are you paying? Do you know how much you're paying? It's ridiculous. So this would not be a function. And that's why it would also be a little bit of a problem for you if you were renting a car from that company. So sequences, like I just said, sequences can be thought of as functions. And we also have sums of sequences could also be thought of as functions. We've come up with that function previously in this class where we added forwards and backwards. And then we came up with a sum. You could do that in general. And you would say add the first and the last, divide by 2, and then multiply by n. That sum is based only on n, which is the number of terms. It becomes a function. So here we are. The sum is this. So this becomes a function of n. You put in the value of n, and you know what the sequence is. Then you could actually come out and say, I know exactly how to find the sum of that. Okay, for one input, you'd have exactly one output. There is a geometric one here. I'm not so sure I'm going to push too hard on the geometric one. It's kind of cool in the fact that it's instead of adding kind of forwards and backwards, you just multiply to find the next term. So multiply by that common difference one more time, and then everything in the middle subtracts itself out, and that's what we get down here. And when you factor, you can turn that into a function of n. So if you were looking at this, you could actually find the sum of the first however many terms you want in a geometric sequence by just knowing the first term, the ratio, and how many terms. So that sum is going to be right there. So for that one, if I gave you a question on that one, you could have the formula for that one. I'd put it on there for you. Okay. Let's see here. There's a sequence one as a function. Let's talk about a composition of functions. I think we're probably going to be getting close to kind of the limit of where we will be algebraically for this class. But again, if you think about the function, if I put 2 into this first function, bump, bump, chicka, chicka, bump, bump, right? 2 plus 4 gives me 6. And then that function falls right back into the next machine. Bump, bump, chicka, chicka, bump, bump. And it's a times 2 machine. So out comes 12. So the way we write this is we are actually finding, the first thing we're finding right here is f of 2. And then that is going into the next function and giving us the 12. So what we really have now is this is g of this input. So it's g of f of 2. And that's what equals 12. Okay. Notationally, if you have these kind of written like this, we write them with this little symbol. And we could actually write it this way. We'd say G composed with F. So F is your starting function. So f of 2. So I put 2, and here's kind of the way you go. I'll change my color real quick so you can see it. Start with 2. 2 goes into the f function. Whatever you get out goes into the g function. It kind of just works its way down. Okay. Yeah, and that also means I know no one has asked that question since I'm talking to myself, but I could certainly have f of 2. Okay. So picture that. 2 goes into the f function, bump, bump, chicka, chicka, bump, bump, right? And I get 6 out. Now take the 6 and put it right back into the function you just did, right? Bump, bump, chicka, chicka, bump, bump. 6 plus 4 is 10, and I would get 10 out of that one. All right. There you be. So that's kind of the idea of composition of functions. I'm not going to do a ton with it. It's kind of, like I said, at the top level in terms of concepts that we could see, but the idea of it is not at the top level. It's like, can I just do this thing again? All right. And that wraps it up for section 8.3. And a lot of this stuff is coming from prior courses, or at least you should have a connection between this and prior courses. I hope that you do. If you do have other questions, please let me know. I can meet with you on Zoom. I can meet with you on campus. I can also make a video specifically about the questions that you may have if you're unable to do either one of those. That's it for now. Off you go.